This is FRM Part 1, Book 2, Foundations of Risk Management, and Chapter 6, Linear Regression with one Regressor. With a linear regression model, we have two variables. And what we believe is that there is some kind of a relationship, whether it's positive or negative, between these two variables. And of course, that must mean that there's some good level of correlation coefficient between the two variables. But the relationship here in linear regression models is a little bit different. What we do is that we separate the two variables. One of the variables we call a dependent variable. The other variable we call an independent variable. And we use the independent variable to explain the dependent variable. Quick example, let's take the number of hours that my children spend on one of their German tests versus their scores on their German test. I mean, it makes sense. It makes sense that what we're trying to do is explain their performance on the exam, so we do it by analyzing the number of hours that they each study. It doesn't make any sense to do it in the opposite direction. So let's look at the learning objectives here. Note that the command or action words are lots of explain and describe and define and summarize and interpret. Interpret's an important one. These don't necessarily sound like calculate or compute, but you ought to be ready to be able to do some kind of minor calculations, and we'll go through these in the slides. All right, so here we go. Explain how regression analysis measures the relationship between dependent and independent variables. All right, so there's what I was describing in that previous slide. We need to interpret the regression function, the coefficients, the slope, the intercept, all that kind of good stuff. We need to interpret it. We need to describe key properties and look at the assumptions of the ordinary least squares method. We need to look at the costs and the benefits of using the OLS estimators, describe properties, interpret the sum of squares, and then interpret the results of an ordinary least squares regression. So let's get started. Here's the good first question. What is regression analysis? Measures how changes in one variable, called the dependent or explained variable, how those changes can be explained by changes in one or more other variables. Now in this chapter we're just using one. This is called a simple linear regression. Later on we'll do multiple regression. So here's a quick example. We could take some independent variables like interest rates and inflation and maybe oil prices and consumer sentiment, all that kind of good macroeconomic variables. What we do is establish the link by forming this regression equation to try to explain the dependent variable. And that dependent variable in this case is going to be GDP, so the size of the economy. It makes perfect sense that if the economy is going like this, then those independent variables are probably doing something, right? If the economy is going like this, then those independent variables are probably doing something else. So in this case, simple linear regression, we just have one independent variable. We're going to say something like, during periods of rising interest rates, this is going to have a specific effect on the size of the economy as measured by GDP. Now let's look at the relationship between two variables here. Let's call this a scatter plot. So all we're doing is collecting data on a y variable and an x variable, and we're plotting them on a graph. All right, so in this case, let's suppose that the return earned by a hedge fund, which is the dependent variable, may depend on the length of the lockup period, which is the independent variable. So we've got that return going up the vertical axis, and we've got the length of time going on the horizontal axis. And just by looking at this, what is that? 2, 4, 6, 8, 10, what is that? 10 or 12 observation points. That's not a ton. We might need 100 or 1,000 to be able to make this work. What are we kind of looking at here? If you eliminate those two at the bottom right, And you can't do that, of course. That's called data mining. But if you eliminate those two on the bottom right, you kind of see like an upward slope there. It's probably going to be upward slope even with those two variables down there. But what the scatter plot does is it gives you a visual. You can look at this thing and you can say, okay, it appears as the x variable goes up, so does the y variable. And remember, we've got to do this on averages. Just like we spent so much time in that last chapter talking about the mean and the standard deviation. Those are going to be important in regression analysis too. All right, so here's the simple linear regression model. So there's the dependent variable y hat over on the left-hand side of the equal sign. And the hat just means that these are samples, not population. And then there's the independent variable over on the x. That's the explanatory variable. And then we have some parameters of the regression model. The first one, that beta hat sub 0, that's always the y-intercept. So that's the intersecting point up on that vertical axis. So that's where we start. And that can be positive or negative. Doesn't have to be either one. Just really depends on the relationship between x and y. And then beta hat 1 is the measure of the sensitivity of changes in y to changes in x, and that's the slope of the regression equation. And that's probably really important to remember, that beta 1 hat is the slope of the regression model, and comma, by the way, that beta there is the beta that you read about in equity securities. And then all the way at the end, there's an error term. My econometrics professor always gave a really, really cool explanation for what that error term is. And of course, the expected value of the error term is 0. You don't ever expect to make an error, but you know that you're going to make an error. And he would say to us, look, you guys can study for 100 hours for one of my tests, but you're not going to make a perfect score on my test, because nobody makes a perfect score on any of my exams, and that error term captures how far away you are from perfection. So I always got the good sense from my econometrics professor that that error term is really important. All right, let's go ahead and put this model into the graph. So there's the y going up the top, there's the x going horizontally. There's the intercept term. Notice that it is a line, right? Simple linear. Line is part of that word linear. So this is an upward sloping. So beta 1 is going to be positive. In this case, the intercept is positive. So there's beta 0 on the left-hand side going up the y-axis. And then there's the linear relationship. And so the slope of the line measures the change in x and the change in y. Beta 0 and beta 1 are known as the regression coefficients. One is the intercept, one is the slope coefficient. Here, getting back to the error term, it represents the portion of the dependent variable that cannot be explained by the independent variable. In other words, it represents effects from the independent variables that are not included in the model. At some point, we'll talk about model misspecification, and it's clear that this is a linear regression, whether it's simple or multiple regression, and you can't really have thousands of variables over there on the right-hand side of the equal sign. So remember, this is not a perfect model, but it's a pretty good model. And so let's swing back to that first example. So here's here in my circle point. So GDP growth is equal to an intercept term plus slope, and times the x variable, which is interest rates there. All right, and so that E term, that error term, it represents the portion of GDP growth that can be explained by variables other than interest rates, like stuff that I talked about earlier, inflation or oil prices, or whether there's a Democrat or a Republican Congress or president, foreign exchange rates, and all sorts of other macroeconomic variables can be thrown in there. All right, let's go ahead and talk about some formulas for the slope and the intercept term. Now, the beta 1 hat, this is by definition. And I bet you remember this from, old-time investment stuff, and even some capital asset pricing model material that we covered earlier. And so beta is always a covariance divided by variance. So it's going to be the covariance between the two variables, right? And remember that covariance can be positive or negative. I showed you how to calculate covariance back in, I think it was just the previous chapter, and then that's going to be divided by the variance of the independent variable. And then you kind of back in to the intercept term. You take that measure of the slope, beta 1 hat, and you throw it into the rearranged version of the equation in which the expected value of the error term is 0. And instead of using all of the x and y variables, you use their means. So beta 0 is equal to the mean of y minus the mean of x, weighted by the slope. And I bet that makes perfect sense to lots of you. Here's some good assumptions of the ordinary least squares model. Expected value of the error term is 0. We talked about that. The observations are independent and identically distributed in the economics terminology. That's called IID. And what that essentially means is that you have think of a big old matrix. You have a constant variance term going down here, and the covariance terms are all 0. Another assumption is that there are no large outliers in the data. I mean, that would occur back in my son's example for studying for their German tests. Like if they studied for 1,000 hours for one German test and made a 5% on it, that would probably be an outlier. Of course, as you know, 14-year-old boys, their brains are not fully developed until they're about 25. So who knows what could explain why they do poorly on their German tests. All right, other assumptions, the error term is normally distributed. So go back up to that first one. So the expected value of the error term is 0, but we know that we're going to make mistakes, right? We know that we're going to make errors, and so the error term is normally distributed, which means, and I'm always used to tilting my head sideways because my professor used to draw that error term normal distribution on the board sideways. And so if you think of it that way, I won't do it to you. Hopefully you guys won't get vertigo. But if you think about it, so that means that all of the error terms are clustered right around the middle. And as you go farther and farther away from the mean, which is 0, you get fewer and fewer observations. Of course, linear relationship exists between the independent and the dependent variable. Independent variables uncorrelated with the error terms. We can talk about serial correlation some other day. And the model does not suffer from misspecification, which includes this no omitted variables. So here's an example. So let's do, what are we doing here? Student-teacher ratio. This is really important in colleges, by the way, and average grade. So let's just look at the data in the box just quickly. So if the ratio is 45, the average grade is 76. If it's 43, it's 77. If it's 40, it's 78. If it's 38, it's 78, and so on and so on. So look, if you go down to like 20, maybe the average grade would be 82 or something like that. So clearly, what does this mean? That the fewer number of students in a class, the better is the performance of the class. All right, and so look at the first bullet point. I say something like, let's suppose we do this 500 different times. And then let's suppose that we get out our little Excel. Excel's pretty nifty, and there are lots of other programs that do regression analysis. But in Excel, it's pretty nifty. And so you just put the data in, go to data and regression, and you'll get, let's suppose we get an intercept term of 90 and a slope coefficient of minus 0.3. So there's the OLS regression line. Test score is equal to 90 minus 0.3 times the student-teacher ratio. And of course, we're not surprised that there's a minus sign in front of that 0.3 because it's a downward slope, and there's the picture there on the bottom right. How about benefits of using OLS estimators? All right, OLS can be said to be the common communication medium as far as regression analysis is concerned. There's lots and lots of ways to run regression analysis, but the ordinary least squares is a part of all these statistical packages, so it's really easy to use. But here's more important, is that these OLS estimators are unbiased and they are consistent, which implies that they are efficient. Remember, we're not asking them to be perfect. My econometrics professor never said, hey, this is a perfect model, it's going to work every time. I mean, rarely do we see this in our daily lives. There are mistakes all the time. Those of you who are football fans will know that back in the NFL playoffs, there was a giant pass interference call that was missed that cost a team a trip to the Super Bowl. Just the other day in the NCAA tournament, there was a double dribble that wasn't called that may have cost the team a chance to compete for the national championship. So we're not looking to be perfect, we're looking to be efficient. And efficient means unbiased and consistent. In talking to basketball and football coaches all over the place, they all will say, all we want is the refs to be consistent. If it's a foul here, then it's a foul over there. If it's not a foul here, it's not a foul over there. I have no idea if basketball and football relate to OLS estimators, but I think it's still a good analogy. How about R squared? What we need to do is to ask ourselves the question, okay, here's a model. We have interest rates and we have GDP. And it makes sense that interest rates would influence GDP. But we need to kind of verify that. We can run the regression. We can estimate a set of regression parameters, but we need to know if this makes any sense from a mathematical or a statistical standpoint. And so this is what we do. We look for the R squared of the regression equation. Look at that second bullet point. It's a measure of the goodness of fit of the regression. So what that means, goodness of fit, means I want you to think about a scatter plot. And suppose you have a scatter plot that goes like this. Can you see I'm going up? I'm going like that. And so that's a goodness of fit. That's a goodness of fit. As opposed to this, suppose you got stuff going all over the place. I feel like I'm Jerry Seinfeld. Everybody can take a reservation. You just can't hold the reservation. All right, so what does that mean? You're still going to draw a line through that, but you're going to have a great distance. I mean, here, this is important. There's going to be a great distance between the line and all of these points. Wow, that must mean that the model's not working very well. So I want you to think about this R squared. Look at my last circle point there. It is interpreted as the percentage of variation in the dependent variable that is explained by the independent variable. All right, so think about an R square of 5%. What does that mean? That must mean that the variability in one of the variables can't be hardly explained at all by the variability in the independent variable. All right, so we're looking for high R squares. Now, comma, by way of definition and interpretation, R square can be rewritten as R times R, and R is the correlation coefficient. And so if you square the correlation coefficient, you get the coefficient of determination. Now, of course, it wouldn't be statistics if we didn't have some good formulas here. So let's look at some of these formulas. So R squared can be expressed mathematically as a ratio of the explained sum of squares. So look at the very bottom. R squared is equal to ESS, explained sum of squares, divided by the total sum of squares. And that should make perfect sense in my example, 5%. Just a few seconds ago, 5% tells us that we probably need to start over. And there are some formulas there. Notice what's going on. What we're doing is we're taking the difference. Notice there are parentheses for both ESS and TSS. So we're taking the difference and we're squaring it. But the difference between the ESS is that we're taking the difference between the Y hat, which is the estimated value of the model, and then in the total, we're taking each individual Y value. Everything else stays the same. It's those Y's that are different. And so you get the ratio of the explained versus the total. So here's a good picture to give you an illustration here. So notice that the regression model is upward sloping. So that's the red line. So we hit the vertical axis somewhere over there going up to the Y. And we've got beta 0 plus beta 1 times x. And those are both hats. And so we've got Y bar. That's the blue line going down. That's the Y bar. And then there are all of the Y I's. There's the purple circle up at the top. And then, so those are the unexplained, and then down at the bottom, those are the explained, and if you sum the two, you get the total explanation. So think of it this way, from purple down to blue, that's the total. From purple down to yellow, that's the unexplained. And then from yellow down to blue, that's the explained. And so clearly, total is equal to ESS plus the SSR, of course, which means that you can rearrange that formula and you can get a different form. You can get a different equation for R squared. Now here's this correlation coefficient, measures the strength and the direction of a linear association between the independent variable and the dependent variable, and it is the square root of R squared, as I said here just a second ago. But remember, here's the cool thing, just like we talked about in the previous chapter, when you compute a covariance, that covariance term can be almost any number, from a minus 4 billion to a plus 643,000 and beyond, right? But the correlation coefficient is the covariance divided by the product of the two standard deviations, all right? So what you do is you standardize the covariance. So you're squeezing it here, just like we did when we were just talking about regular old stats in the previous chapter. Here we're doing it when we have a dependent and an independent variable. So we're going to squish it down to a more palatable range. And so if there is no linear correlation, then the correlation coefficient is going to be 0. If it's negatively related, we move all the way over to a -1. That means perfect negative correlation. And that means that when one variable does something, the other variable does just exactly the opposite. Okay. And then, of course, positive correlation. So as we move from 0 out to +1, that's increasing degree of positive correlation. And there's a picture of what perfectly positive two variables looks like. The standard error of the regression measures the degree of variability of the actual y variables. So think about those variables back in our student-teacher to performance on an exam example. So the actual values to the estimated y values. And so that's kind of like the standard error measures that variability between those two. So if the R squared is 100% and correlation is going to be 1, then that must mean that we have a perfect model, which of course we never do. So notice in my first circle point there in the middle, the smaller the standard error, the better the fit. So you're probably never going to get a 0 standard error because relationships are not perfect. Now, this can also be referred to as the standard error of the residual or the standard error of the estimate. And that takes us through linear regression with one regressor.